Welcome back. We'll continue where we left off, looking at other reactions of alcohols. One thing we can do is standard SN reactions. Standard SN reaction. So, for example, we can replace the hydroxide with a halogen. We add hydrobromic acid, example, in the presence of water, and we can replace that with RBR, and we form water as a byproduct. How is that going to work? You simply you protonate base, you make a good leaving group, and then you nucleophilic substitution. Now, the method depends on what type of alcohol you have. Tertiary is just going to work by SN1. So, secondary, tertiary, so is secondary. Secondary is going to work by SN1. The primary will work by SN2. Now, what's the general mechanism? Just a quick reminder. Here's for tertiary of alcohol. Presence of an acid, HBr, pair, tax there, kicks that off. You have your protonated water. It's now a good leaving group. Electrons go with that. We lose water. Suddenly we have our planar byproduct, the tert-butyl cation, and now bromine can now attack either from the top or the bottom. Primary is forced to do backside attack. Primary still undergoes the same first step of acidify the alcohol to make a good leaving group. But the leaving group does not leave until after the bromine attacks. So we're going to see a backside attack before we kick that off, as is determined by standard SN2 reaction. So nothing too complicated here. So you could do this with concentrated hydrobromic acid, or you could do this with sodium bromide and a strong acid like sulfuric acid. Sulfuric acid, not a very good nucleophile. Sulfate, not a very good nucleophile. So sodium bromide and sulfuric acid, or just concentrated hydrobromic acid, one way to do this. You could also do this with, so okay, concentrated HBr or NABR. You could do this with HCl. So, but HCl is weaker, is a weaker nucleophile. So we actually add a Lewis acid. So a Lewis acid helper. So it needs Lewis acid to help. So our Lewis acid in this case is zinc chloride, which will allow for substitution to both tertiary, secondary, and primary. tertiary and secondary will still react with SN1. But so the reaction here, a little crazy, a little bit stranger. So OH first will attack the zinc. Zinc is going to provide a better electrophile than our proton in this case. So we have, in this case, zinc, Cl, better for handling this. And we actually see the loss of a, sorry. See the loss of this group. So we have a zinc hydroxy zinc chloride. And then you can see the Cl minus attacking there. Do a similar thing with the secondary. Similar thing with the secondary. Primary undergoes SN2. Primary is SN2. So, and once again, from this step, a primary alcohol, I'm just going to draw at this step. CN would undergo backside attack by Cl minus before this falls off. So I don't think that it's really too complicated. It's just a SN2. It's just because chloride is a weaker nucleophile, we need a little bit of a helper to help along. Now, this particular test has a name. The nursing chemists learn this if they do this in lab. But it's a name that's very useful for testing for what type of alcohols you have. It's called the Lucas test. It's you're essentially adding HCl and zinc chloride. You add the Lucas reagent, and you can tell what type of acid you have, or what type of alcohol you have based on the results. That tertiary is essentially instantaneous. Instant. The second you add this, the second you, what is going on here? The second you add it, it reacts. You don't really notice a lag time. Secondary takes anywhere between 1 to 5 minutes. Primary is going to be usually longer than 6 minutes and often needs heat. And we'll need our heat to make this work. So you can tell, oh, what type of alcohol do we have? Primary, secondary, tertiary, just by adding this in and looking for the byproduct. However, there are some problems here. There's some trouble in paradise here with our HX addition to hydroxide. to our alcohol group. 1. We get 4 yields in primary and secondary with HCl. Yields. This is due to the slowness of the reaction. We can often get, remember, elimination side reactions. We have to worry about just because we've made a good leaving group doesn't mean it's necessarily going to go through nucleophilic substitution. We can often see in secondary and primary, you could see rearrangements, especially in SN1. We're always going to try to make the most stable carbocation. And of course, it's going to be a difficulty, hard to make a RI bond. So far, we've shown how to make a RBr or RCl, but not a iodine. So that's why HCl and HBr, you can't make an HI through that way. We can't use HI in that way. But however, there's a way to do this with a simpler using phosphorus. We can use PX3 as our thing. And essentially, most of these are stable, but all are most of these phosphorus halides are stable, but all are very reactive. So I could do 3 equivalents of our alcohol with PCl3, and we're just going to form 3 equivalents of RCl and phosphorus trihydroxy. You could do this with the same thing with Br, PBr3. No problems there. Or we could do this with, instead of PCl3, we could do this with PCl5. H plus PCl5 will give you just 1 equivalent of RCl. We'll get some POCl3 and HCl. And this one is the most interesting. 6ROH plus 2 equivalents of phosphorus and 3 equivalents of iodine will give us 6 equivalents of Ri and 2 of POH3. I mean, essentially, you're getting 2 equivalents of PI3. The reason I've split it up into P and I2 is because PI3 are kind of reactive and not really stable. You can't hold them in solution you can't hold them indefinitely like you can PCl3 or PBr3. But these all guys work with primary and secondary, but not with tertiary. So, primary, secondary, but not with tertiary. And this is most often used with PBr3 or with our iodine. It's better than the HBr because it avoids some of the rearrangement, and the mechanism for PCl, PBr, and PI3 are all very similar. They work via SN2 with no carbocation. So that's part of why we will not see tertiary reactions. But so what's happening? We have R, O, H. We have our P, we have a Br. So this is the Br3. We have a lone pair on here attacking there, kicking off a bromine. So we now, from there, we have our R, O, H, P, R, dot, dot, and now the bromine can now back attack that guy, kick off that group. And so now we have our Br, and we have, of course, OH, P, Br, Br. So this can keep doing this so long as it has bromines left. Once we've replaced all the bromines, obviously it goes away. Another way to do this is with thionyl chloride. Thionyl chloride is going to replace the alcohol with chloride. So ROH plus, so thionyl. Thio means sulfur. So the thiol group of the tosyl, well, so thionyl chloride. We add heat, and we're going to form RCl. SO2 is a byproduct. It's going to leave an HCl gas as a byproduct. Now, the exact mechanism of this depends on whether this is primary, secondary, or tertiary. Primary is going to be like, so let's look at that one. Let's see, let's erase some of this. The mechanism is kind of interesting. But basically, it all comes down to the alcohol acts as a nucleophile to a really strong electrophile. That's pretty much all of these guys come down to. Yes, there's a lot of different mechanisms, but it's like the alcohol acts as a nucleophile to a really strong electrophile. We started off with HBr, and the alcohol attacks the hydrogen. In the Lucas test, we said the alcohol attacks the zinc. And the phosphorus, the alcohol, the oxygen attacks the phosphorus. And now we're attacking, the alcohol is attacking the sulfur. These guys that, because of their lower structure, can accept these extra electrons. So we form our species like thus. Minus, then this O minus swings back down, kicks off a better leaving group, kicks off the chloride. From there, R O plus H O Cl. The chloride can deprotonate the alcohol to form this guy. Now this guy is a particularly good leaving group. Now, depending on whether this guy can leave. And now depending on what mechanism you have depends on whether this is like a SN1 or a concerted step. So you essentially have a R plus, and before this even really gets away, essentially this bond swings over here from chloride, and this lone pair swings down to form an SO2. And this becomes a really fast step. So once that breaks off, it's almost instantaneous to get to the next step, where RCl plus SO2. So it's a quick review of all the different types of things. If I want a primary, secondary, or tertiary alcohol, what I want to add, the ways we can do this. Br. So primary, SOCl2 is probably the easiest. SOCl2 is probably the easiest. HCl. Primary, PBr3 or HBr, but with reservations on the HBr. PBr3, HBr. Gotta watch out for rearrangement. P and iodine for primary, P and iodine. It is possible to do this tertiary with hydroiodic acid. So those are just the various ways. On most of the cases, it's much better to use the alternatives. Okay. So a few other things. Alcohol dehydration. So we kind of went over this very briefly, but what's going on? We've seen this before. There's a E1 alcohol dehydration. Almost all of these reactions start with when we're removing the alcohol, we're starting by pronating the alcohol. So in the presence of strong acid, attack here, form a good leaving group. So kick that off. Depending on whether this is E1 or E2, kick that off. Carbocation, H, our water. Pronates that, and that swings down. We form our alkene. Yeah. With E1, rearrangements are common. So primary alcohols can hard to do. Need very strong conditions. Typically Zaitchev's product is favored. So that's the most highly substituted. Let's say E1 rearrangement. E1, just put notes, E1 rearrangement common. Common. It's always going to try to form the most stable carbocation. This is going to happen more commonly. I mean, is tertiary alcohols are going to react better than secondary alcohols, which are going to react better than, much better than primary alcohols. We see a lot of rearrangement and very poor yields when we deal with the primary alcohols. And we always have to follow Zaitchev's rule. One thing we can see, though, is a bimolecular. Okay, that's just all I have down for that. There's not a whole lot there, but that's just one type of reaction we can see. Another type is ether formation, or also known as bimolecular condensation. Molecular condensation. Break that down. Two molecules come together to form one via water loss, condensation. How does this work? Step one, we add the acid. We make a good leaving group. Step two, alcohol attacks. Step three, we're going to remove the extra proton to regenerate the catalyst. So, for example, OH, in presence of acid, we protonate here. Suddenly now we have a good leaving group. Now another alcohol attack here. Kick that off. So, cation, and then of course our water. Grab that. Swing it down. So, all said and done, the final product is an ether. We formed an ether by combining two alcohols together. Typically, a condensation reaction is combining two molecules, but loss of the third. Typically, a condensation reaction can compete with an elimination reaction. So this alcohol could attack there, or it could attack adjacent to there, beta to that position. Now, the last thing I'm going to talk about today before actually, no, I'll keep going. We're going to look finally at some esterifications and some other ether esterifications. This is one of the next things. So ester, remember an ester is when you combine essentially a ether with a carbonyl group. One of the most common things is called the Fischer esterification. It's a reaction similar to the condensation that we just saw. We're going to combine an acid with an alcohol. And the byproduct is going to be, in the presence of acid, and the byproduct is going to be our ester. And of course, water. Now, this esterification is an equilibrium reaction. So it's often unfavorable. So how do we favor this product? Well, equilibrium, or Le Chatelier says, add to the left, it shifts to the right. So either an excess of the acid or excess of the alcohol is often used. And that forces it to shift to the left. Another way would be to use an alcohol and an acid chloride. Acid chloride, as we'll learn later, is a much more reactive version than a alcohol, than an acid. And so this is less likely to go backwards. It's a much, the chloride is a much weaker leaving group. So using it, and the only problem is we have to be careful what solvent we use it in, because water would then react with acid chloride and turn it back into an acid. So we have to use a polar aprotic solvent. So and you just have Cl minus, well, HCl. Well, no, it's Cl minus, and you form pyridinium. Essentially saying acid chlorides react with water. So how do you avoid reacting with water? It's going to react with water to form an acid. You use a polar aprotic solvent, the same way as when we use a polar aprotic solvent when we use Grignards, because Grignard will react with water. Now there's some other esters that do some similar things. You can have some inorganic esters, like the form the Thionyl Chloride. Remember that? We did that. We can do the same thing. ROH, that was essentially Esterferication. HOSO. The forming of the tosyl group. Was essentially this Esterferication. We pronate and make a good leaving group, and then that comes in and adds that. Now we have even better leaving group. Or using the tosyl chloride, TSCl, to form the RO. Sure, as a byproduct first. HCl is a byproduct. We could do it just with sulfates. You could do sulfate esters. Sulfates are actually excellent leaving groups. So you could do this with ROH and H2SO4. And you're going to first form ROSO. OH, and then you can do it again with another ROH and have it on the other side. So you have ROS, and then you can suddenly now have an excellent electrophile for a nucleophile, a weak nucleophile to add to. So in this case, if I added ammonia, H3, I could form NH3 ammonium alkane, because sulfur is such a darn good leaving group, which is why the tosyl group is so useful. You could also do the same thing with nitrates. So nitric acid, for example, you could use that to form a nitro group. Just a quick picture of that. So ROH plus a HO NO. is essentially going to form RO and water, form a nitro group. Essentially, nitroglycerin. How you can form nitroglycerin through this process. You could also do a phosphate esters, same way. Like RH with H3PO4 essentially is going to form, if you do 3 equivalents, you're going to have 3 equivalents of water, and you're going to have phosphorus, OR, 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 and 3 waters. But they're all essentially the same mechanism. So that's why I'm kind of waving my hands. I'm not showing the dang mechanistic step each time. It's protonate the alcohol. You now have a good leaving group for a nucleophile to come in and kick it out. Well, these are just different esters of the same thing. Now, the last 2 things, last major thing I'll talk about in this chapter is alkoxides. Forming alkoxides from alcohols, and then a few reactions of alkoxides. Alkoxide, remember, is the OH without the H. So in this case, I'm cleaving the OH bond instead of the RO bond. So in this case, adding sodium, for example, is going to give us alkoxide. It's a alkoxide and our hydrogen gas. So half equivalent of hydrogen gas. Now we could do the same thing with, remember, potassium. Talked about this in my little review, the various different reactive mechanisms. Have hydrogen. But for formation, methyl is going to be easier than primary, which is easier than secondary, which is tertiary. Potassium is more reactive than sodium. I think when we talked about it before, you could easily use sodium for primary and methyl, and then potassium will work with pretty much all of them. And we can also use sodium hydride for which is even more reactive than the other guys. So look at that real quick. ROH plus NaH. Once again, this is so reactive, we have to use a polar aprotic solvent. So we're going to use THF. We don't want to accidentally react this with water. We want to have this stick around till we. So now, what can we use this for? I'm going to finish this off with a reaction called the Williamson ether synthesis. Williamson ether synthesis. This is a way. It's not like the condensation one. It's going to be alkoxide plus halide, RX to form ROR. And this works by SN2. And it's usually for primary. So basic premise here is I take some alcohol. I add my sodium or potassium or sodium hydride, form my alkoxide, RO minus, Na plus, and my half equivalent of hydrogen. Now, by making that, we've essentially formed an incredibly strong nucleophile, which is then going to backside attack, kick off the halogen. And so now we formed our RO. So please note, the alkoxide does not have to be primary. Alkoxide does not have to be primary, but the halogen has to be primary because it's a backside attack on the halogen. So secondary doesn't work nearly as well. Tertiary doesn't work at all because you were trying to get this without forming the carbocation. So it's a really easy way to click two different compounds together. And depending on what you need, depends on what metal you use to form the alkoxide. But okay, that's the end of the chapter of all the various reactions we have for alcohols. The next chapter we'll look at is dealing with ethers, epoxide, and thioethers. Thank you for watching.